let's examine some more spectra and see if we can figure out what the molecule is. Here we've got a number of things. This is from NMR Assignment number 1, and it has an IR, the proton NMR, and the C13 NMR. What you're going to find out as we go through these is C13 NMRs tend to help, but oftentimes we can figure out what's going on without them, but that's good information. Also note, this is actually the molecular weight is 130. This has 130 grams per mole. That's the molar mass right there. All right, the first thing we need to consider is the IR. What does the IR tell us? Note, does that mean anything? It's not very deep. So could be an NH, could be OH maybe. It's broad, but we'd expect those to be kind of deeper if that were the case. So right now, I'm not saying that's anything, but I'm keeping it in mind. All right, normal C bond, this is just normal, a carbon bonded another carbon, hydrogen. It's the CH stretch of a single bonded carbon, so that's nothing. Ooh, but what do we have here? 1741 wave numbers. Okay, there's some good stuff there. There's a carbonyl. And let's see, what else do we have here? Ooh, see, I've got this big peak right here at, what is that, 1190 or something like that, and it's kind of wide, and it's almost as deep as this carbonyl peak. Now, I could be wrong, but to me, when I see this carbonyl peak and this wide peak right there, I'm thinking this is a carbon and oxygen bond, and I am right now thinking ester. I have seen this pattern before where I have two peaks that are a little bit broad, one at 17 something, one between 10 and 1200 wave numbers. This just looks to me like ester. I could be wrong, but that's a pretty sizable peak to be similar in size to the carbonyl peak. So I'm looking at that. All right, okay, let's go down to the proton NMR, because truthfully this is where we're going to do most of our work because it gives us most of our information. Again, I like to start on the left. I like to start downfield, work my way upfield, and I've got it. Resonance here integrates to 2. It's a triplet down at 4. Remember, integration, spin, splitting, chemical shift are the three things you look at. Integration, well, I think this is a CH2. That's the most likely thing to integrate to 2. It's a triplet. Tells me there's probably a CH2 next to it. And it's down at 4 ppm. What can bring it down to 4 ppm? I am guessing an oxygen. That oxygen will bring it down to 4. So my first guess for that peak is that. Okay. Let's move on here. 2 hydrogens. Well, that's probably a CH2. Oh, it's a quartet. Why is it a quartet? Well, that means there are 3 hydrogens next door. And at this point, I could say, well, how do I get 3 hydrogens next door? Well, the most obvious way is a CH3 next door. That'll work. However, it could be that the CH2 has a CH on one side and a CH2 on the other. Because a CH and a CH2 will also give us 3 next door and give us a quartet. And the good news is, right now, we can just look and say, no, this is not possible. How do I know that's not possible? Because if this was a CH next door, I would have a resonance in here that integrated to 1. There's no resonances in here that integrate to 1. Therefore, this isn't the deal. Cool. Note it's also at 2.5 ppm, 2.4. What's going to bring it downfield to 2.4 ppm? And truth be told, where beginners tend to mess up in NMR spectra is not considering chemical shifts. What's going to bring it down to 2.4 ppm? Well, if it was next to an oxygen, that would bring it down to 4. If it was just next to other CH2s and CH3s, nothing else, it would be down 1 to 2. So the only thing that would bring it to above 2 ppm that we have already figured out is in our molecule is this carbonyl. I'm betting you the carbonyl is right here. Okay. And note, because of this, because I'm pretty confident in that, I know this CH3 is one of these CH3s. Either this one or this one. Integrates to 3 and is a triplet, so it means there's 2 next door. I'm betting I've already taken care of this CH3 there also. Or one of those two. Alright, well, what do we have left in here? Well, we've got a couple of CH2s that we haven't looked at and another CH3. I'm guessing, well, CH3, yeah, this guy right there, kind of moving off. This is a CH3, CH2. And let's look at these two guys. What are these telling us? Well, let's see. Integrates to 2, CH2. 1, 2, 3, 4, 5. I'm counting 5 peaks there. Are you counting 5? So that would be 4 neighbors next door. How do you get 4 neighbors next door? 2 CH2s. It could have been a CH3 and a CH, but as we already said, we cannot have a CH in here, so this is the most likely way for this peak. Let's look at this one. Okay. That's another CH2, but it has 1, 2, 3, 4, 5, 6. 6 peaks means 5 neighbors next door. Probably a CH2 and a CH3. That's how we can get 5 neighbors next door. Now, at this point, you were probably saying, what the heck is what, huh? I'm looking at this and, oh my goodness gracious, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a lot of carbons in this in here and lots of hydrogens. Realize NMR gives us redundant information, so we have to figure out where the redundancies are. Okay, we're pretty confident of the carbonyl CH2, CH3 that this peak gave us. So that's this CH2 and one of these CH3s are taken care of. We know we have an OCH2, CH2. Well, this CH2 is this one. Where is this CH2? It's got to be one of these two. So that's, so that's one of these guys here. And since it's CH2, it's this guy. It's that CH2. And realize that then this CH2 here is this one, which is the same as that CH2. Because we know this one is a CH2 next to a CH3. So, okay, let's add all this up. I've got a CH3, CH2 here. CH3, CH2. Over here I've got, CH3 and this CH2. Over here I've got this CH2, the next CH2, and I still have to do a CH2 and a CH3. So I know this piece of the molecule will be OCH2, CH2, another CH2, and a CH3. And so here are my pieces now. This piece and that piece. Let's double check. Before we put this together, I see 2 CH3s. 1, 2. How many CH2s? 1, 2, 3, 4. 1, 2, 3, 4. Yes, I have not doubled anything. I've got 2 CH3s. I've got 4 CH2s. And so at this point, my best guess for this molecule, or my current thinking, is CH3, CH2, C double bond O, O, CH2, 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 CH3. But if this were the molecule, the masses would add up to 130. So let's do a little bit of math here, shall we? I've got 1, 2, 3, 4, 5, 6, 7. 7 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 hydrogens, 2 oxygens. And when I add up all those masses on the calculator, I get 130. So that tells me there's no extra oxygens in here or anything missing. This works out. So this is the molecule right there. Yeah. Although CH2's made it a little tricky, but we could figure out. And check it out. It is an ester. Just like the IR kind of led me to believe. All right. Whew. That was fun. Let's do another one. Okay, what does this tell us? Well, molecular weight is 116, gotcha. We've got our IR, and our IR is telling us, what is it telling us here? What is it telling you? I'll tell you what it's telling me. I'm seeing carbonyl. I'm seeing another peak right here that's about the same, that's also wide and about the same length. This is screaming ester at me again. I should have a carbonyl, and this is the carbon single bond oxygen of an ester, and I'm not seeing anything else there. I don't see any double bonds or anything like that, nothing crazy. No benzene rings, so I'm looking at another ester is what I'm thinking here. Let's look at the proton NMR now. All right, well, let's start over here. Well, we've seen this before, and I tell you what, the best way to get better at NMR is just do it over and over again, because you see things that you've seen before, and it makes it much quicker to figure out what it is. Integrates to 2, it's a triplet, down at 4. We saw that on the last one. That's an OCH2CH2. All right. Ooh, let's look at this. Integrates to 3 and is a singlet. Well, only one real good way to get that. That's a CH3 bonded to something, and whatever it's bonded to had to move it down to about 2 ppm and has no hydrogens on it. Well, could it be this bonded to this O? No, it couldn't be bonded to the other side of this oxygen, or else it would be down about 4. What moves something down to about 2 ppm and contains no hydrogens on it? A carbonyl does. So I'm betting you the carbonyl is bonded there. And at this point we're looking, okay, well, what else do we see here? We got 2 CH2s and a CH3. Just 2, 2, and 3 tells us 2 CH2s and a CH3. Note, one of these CH2s is this guy. So I know with my CH3 here, I have to have CH3 bonded to a CH2 because it's a triplet. So let's see. What do I have? Let me look at my pieces. 2 CH3s, 1, 2. 1, 2, 3 CH2s. 1, 2, 3 CH2s. These are the pieces of my molecule, and there's only one way to put them together to make a molecule. CH3, C double bond O, O. There's my ester, yay. CH2, 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 CH3. Let's double check. How many CH2s? 1, 2, 3 CH2s. 1, 2, 3 CH2s. I got that from the integrations. 2 CH3s. 1, 2 CH3s. We got my carbonyl in there. And if you were to add up 12 for carbon, or the mass of the carbons and the oxygens and the hydrogens, you will find that this goes to 116. Phew. Well, we've got 2 more to go. Let's grind through them. Let's do them. Okay. So let's look at this beast here. A molar mass molecular weight of 136. Ooh, the IR is looking happy, because what does this tell me? That's an OH. I know I have an OH in here. All right. Yeah, the IR is also telling me I've got some junk in here down to the slightly to the left of 3000 wave numbers. And so I'm betting there's double bonds and stuff in here, but I know I have that OH. Note, no carbonyls. There's no carbonyls in here, so I don't have to worry about those. Look at the proton NMR. Well, look at here. 7. What can bring something down around 7? That's right, a benzene ring. But this is a little special here. I know I've got a benzene ring, but let's look at the pattern here. I've got a doublet and a doublet, and each doublet integrates to 2. There's only one way to get a really clean-looking doublet that integrates to 2, and another clean-looking doublet that integrates to 2 down around 7 p.m. That is what we call a para-disubstituted benzene ring, where one substituent, we'll call that carbon 1, 2, 3, 4. A 1,4 disubstituted benzene ring gives this pattern. If you had substituents in other places on the benzene ring, you would not get this pattern of these 2 doublets looking like that. There's something else that a lot of people don't tell you about, but I will because I think you're worthy. It's that whenever you see a benzene ring and you see resonances of a benzene ring come a little upfield of 7, 6.8-ish or so, that almost always indicates that there's an oxygen or nitrogen bonded to the benzene ring. Every time I have seen NMR resonances belonging to a benzene ring upfield from 7 a little bit, there's always been an oxygen or a nitrogen bonded here. So there's either, I bet, an oxygen or a nitrogen bonded there. I don't know for sure, but that's my guess. That's what I'm looking for. All right, so let's move down. We've got a peak at 4.8 ppm. It's a singlet, and I have no idea what that is. Okay, let's move on. Let's not worry about it. Oh, wait a minute, because I know what this is. What do I have screaming at me right here? Wait, integrates to 6, and it's a doublet, a multiplet. That's an isopropyl group. This is screaming isopropyl at me. Yes. Okay. And so I've got my para-disubstituted benzene ring for sure. I've got my screaming isopropyl, got that, and what else is there? Ooh, I know there's an OH. Okay. I know I've got an OH from the IR. But I don't know what that is. But wait a minute. This hydrogen has to be somewhere. The hydrogen of the OH has to be somewhere. That's probably what that is, because there's no other resonances in here. So this must be the hydrogen of that OH. Who knew? Well, I guess that's the way it goes. Not only that, but look at my pieces parts. I got counting my carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Count up my hydrogen, 6, 7, 8, 9, 10, 11, 12, and my oxygen. When I add the masses of all those pieces parts, I get 136. Which tells me I just have to assemble my molecule. I've got these 3 pieces. Well, it becomes obvious now. This OH is on one of these, so one of the positions on the benzene ring, and the opposite is the isopropyl group. That's my molecule. It works with the spectra, it works with the mass, and not only that, I've got its oxygen bonded to the benzene ring, which I figured was going to happen because I've got a resonance upfield of 7 ppm. All right, one more to go. Let's see what this last one looks like. All right, molar mass is 130. Gotcha. And okay, IR is telling me nothing. There's nothing fun here. There's no OH or NH. There's no triple bonds. There's no aldehyde here. There's no carbonyl. This is just carbon hydrogen stretches of single bonded carbons. Well, 1122. That's a pretty wide peak there. Maybe that's something, but that's fingerprint. I don't know. Maybe we'll have to come back to that. Now we look at the proton NMR. And first of all, I'm seeing really funky integrations. And I don't worry about funky integrations because I've got 1 to 1 to 1.5. And I know we can't have a 1.5, so I'm just going to scratch these out. This has to be 3 to 2 to 2 to 2 because I can't have a 1.5 proton. So the smallest this can be is twice that 3. So I'm looking at 3 to 2 to 2 to 2. And then I've got things I can deal with because look at this right here. I start at the left. It integrates to 2. That's a CH2. It's a triplet. Probably means there's a CH2 next to it. It is down at 3.5 ppm. And what can bring it down to 3.5 ppm? Well, really, there's only 2 things that can do that, an oxygen or a nitrogen. I'll give you a little hint. I don't think it's nitrogen, and I'll tell you why. Its molecular weight is 130. That's an even molecular weight. If your molecular weight is even, that means you have either none or an even number of nitrogens. It's just one of those things that if your molecular weight is odd, that equals 1 or 3 or 5 nitrogen atoms. And you rarely see 5. You don't even see 3 that often. So an odd molecular weight would mean you have 1, maybe 3 nitrogens in your molecule. An even molecular weight either means no nitrogens or maybe 2 nitrogens for your average molecule. And the fact that it's a molecular weight of 130 and I don't have anything that would indicate NHs in here, in my IR, I'm just really doubting that there's any nitrogens in here with that even molecular weight and no NH stretches. Okay, so I am betting that the thing that's bringing this down to 3.5 ppm is an oxygen. Realize, and this is not going to make you happy, that I could be completely wrong. But if I am completely wrong, there will be something in the rest of the molecule NMR spectrum that will show me that I'm wrong. It's like, oh, okay, that's not going to work. And this is how you do. You have to just go with the most likely thing it is, and sometimes it's not that, so you have to change it up. But it's best to start out with the most likely, and most likely is oxygen, not nitrogen. Bring it down to 3.5. Okay, moving down. Integrates to 2. That's a CH2. What's on the other sides of it? Ooh, check out the splitting. 1, 2, 3, 4, 5. Does that guy belong with this one? Does it belong with that one? I have no idea. It's right here. Does it belong with this one, or does it belong with this one? The fact that it's small and roughly the same size as this one, I'm thinking it might belong to this one, but I can't be sure. So what are the possibilities? Well, 1, 2, 3, 4, 5. 5 peaks, which means this guy sees 4. Well, that'd be a CH2 and a CH2. Or 1, 2, 3, 4, 5, 6 peaks, and this guy sees 5. That would be a CH2 and a CH3. Note, if this guy belongs to this one over here, that's 1, 2, 3, 4, 5, 6. That would be a CH3 and a CH2. So the good news is we don't have to worry about this, because whether this one belongs to here or to here, either we have 5 peaks and 6 peaks, or 6 peaks and 5 peaks. They're both CH2s. Either way, that's telling us we have a CH3, CH2, CH2, or a CH2, CH2, CH2. Okay. Now, we got redundant information, so okay, there's that CH3 there. Let's assume that this peak belongs with this one, so here's this CH3 is this one, this CH2 is this one, this CH2 is that one, this CH2 is that one. That means this one and this one were the same. And, okay, this is telling me OCH2, CH2, CH2, CH3. 1, 2, 3 CH2s and a CH3 and an oxygen. Okay, and that's what I'm betting so far. The problem is, what's on the other side of that oxygen? I don't know what's on the other side of the oxygen. Where do we go from here? Oh, let's check it out. Maybe there's a chlorine, maybe. Who knows what's on there, but I bet our molecular weight might give us some information. We have a molecular weight of 130. How much mass of that have we come up with so far? Well, let's take a look. If I 1, 2, 3, 4, 4 carbons. That's 48. 1, 5, 4, 9, 50, 51, 52, 3, 4, 5, 57. So this part gives me 57. Oxygen is 16, so 57 plus 16 is 73. All right, check my math there. I got 73 for this. Add that oxygen in there, we get 73. But I know my mass from up there is 130. So 130 minus 73 is, carry the 57. So somehow I'm missing a mass of 57. But it's weird because I only have 1, 2, 3, 4 carbons showing. Here's all my hydrogen. So what has a mass of 57 with no carbons or no hydrogens? And then we realize, oh, but what? I've seen that mass of 57 before. Where have I seen this 57? It's this. It's the mass of a butyl group. What this means then is what's on the other side of this oxygen? Another butyl group. So this molecule is actually CH3, CH2, 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 O, CH2, 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 work it in here, CH3. It's a butyl group, O, it's a dibutyl ether. Having symmetrical molecules is what really will give you fits when you're first starting solving NMR spectra. Because how would you know it's symmetrical? What told me it was symmetrical? There's nothing. But we just happen to realize, oh, what's the mass that is missing is the exact mass of this part. And we realize if this molecule has a center of symmetry, this side is the same as that side. Therefore, these two CH3s come at the same chemical shift. These CH2s are identical, these CH2s are identical, these two CH2s are identical. So the whole molecule is symmetrical, so the NMR only show you half the molecule because the other half's identical. That gets tricky. So just something to watch out for with that. All right, keep practicing in your on Canvas. We've got 22 NMR problems. Just keep working on these. The only way to get better is just to work and work and work and work. If you tried to do these 4 molecules and it took you longer than 2 hours, don't worry about it. That's how long it takes. Eventually you'll be able to get all 4 of these in less than 5 minutes. If you take organic 2 and you keep working and working and working. Till then, good luck.